Hello and welcome. In this video, we're going to be building something called the Lewis structure. The Lewis structure will be the basic skeleton of a molecule. It'll show how all the atoms are bonded together, and you'll get a good sense of what the molecule looks like. To get a true sense of what a molecule looks like, we would need to use a theory called VSEPR. It's kind of spelled VSEPR. That'll give you a true sense of the geometry and the angles involved in a molecule. That would involve something like model kits, building something like this. But we're not doing this yet. That's going to be the next video. All right, so the previous video we talked about Lewis symbols. We're doing this second step of Lewis structures. VSEPR will be a future video. All right, so this is how we build a molecule as a Lewis structure. I like to cover it in 6 steps. It's very important that you follow this order of building your molecule, especially if you are totally new to building molecules. After you have enough experience, you'll be able to kind of do this all at once and anticipate some things. But until you reach that point, follow this in order. Step number 1 is to count your total number of valence electrons. But before you do that, you're going to remove all the valence electrons from all the atoms. Once you remove them, then you just count the total that you've collected. Number 2 is to choose a central atom. Choose your center atom. Often that's going to be your highest bonding capacity atom. Often it's going to be your largest atom. Often, practically speaking, it's going to be the first element listed. All right, and I see sometimes people write it's often your least electronegative element. And I mean, that kind of ties in with element largeness. Okay. Very importantly, it's never hydrogen. Hydrogen is never your central element. Okay. H stands for hydrogen. H also stands for happy. All right. The moment you draw a bond to a hydrogen atom, it's done. It's happy. It does not get anything else. Hydrogen follows a duet rule. You see, when you draw a bond counts as 2 electrons. That hydrogen is done. Okay. Don't draw 2 bonds on hydrogen. Don't draw 3. Only 1. Okay, so we've chosen a central atom. Then we're going to build single bonds from the center atom to each outer atom. So if we had a molecular formula like H2O, water, you'd have an oxygen in the middle, put your hydrogens on the outside, and then you draw a bond to each of the hydrogens. And each time you spend or make a bond, you have spent 2 electrons. So at this moment, we have just 4 electrons remaining. This is kind of a game of spending. All right. Number 4 and number 5 show an outside-in approach. All right. With remaining electrons, you're going to distribute them to the outer atoms in pairs. Okay. Only until octet is achieved. Okay. So I'm going to write here if needed. Okay. Until octet / duet. All right. Hydrogen follows, gets its duet instantly when you draw a bond to it. So in this example molecule, hydrogen, both of these hydrogens don't need any more electrons. All right. Number 5, distribute remaining valence electrons to the center atom. And again, we're going to work in pairs. This oxygen needs 4 more on it. I have 4 more left to spend. Boom, 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 boom. Okay. And then number 6, we don't need it for this molecule, but it says convert outer atom lone pairs into bonds. When you do this, it'll create a double or triple bond. Okay, we will have some examples of that later. All right. So that's kind of the overview of the rules here. I have it in a summary form. Okay. Valence electrons. Center atom, single bonds, outer octets, center octet, double, triple bonds, steps 4 through 6 only if needed. Remember to follow the steps in order. All right, so that's a review of the steps. The majority of this video is going to be examples. I feel like the best way to learn this and to really get a feel for how to do the process is to do many examples from many different sorts of cases. All right, so that's hopefully what you'll experience with this walkthrough. All right, so you have some options here. You could look at this slide here. You could pause for a little bit. You could write these down. And you can try them out immediately. Another option would be to just kind of learn from watching as I go. And maybe a middle option would be watch a few, do a few with me. And then once you feel like you kind of have a process, then hit pause, try the rest of them on your own, and then compare with what I did. Okay, so giving you a minute to look at these. Okay, I'll just read each of the formulas. We have CH4, NH3, H2O, CCl4, CHCl3, NCl3, NH2Cl, HOCl, CH2O, CO2, H2, Cl2, O2, N2, SO2, and CO, carbon monoxide. All right. Let's go ahead and begin. All right, so first up we have methane, CH4. So we want to count the total number of valence electrons. We have 1 carbon, we have 4 hydrogens. Go to your periodic table and figure out how many valence electrons you have for each. All right, I'll give you a second. Okay, here's my periodic table. We see that carbon is in the 4 valence electron column. Hydrogen is in the 1 valence electron column. So our math would become 1 times 4 and 4 times 1. All right, let's add these together and we're going to get a sum of 8 valence electrons. Very important. It's very important that you get your total correct. If your total is wrong, then everything else will get messed up and you'll have the wrong structure. Okay, so time to choose a central atom. Well, it can never be hydrogen. Carbon is a good central atom. C stands for center in my mind. All right, so we've chosen our central atom. And we're going to put all of our outer atoms on the outside. Okay, for many structures, especially at the Chem 101 introductory chemistry level, it's helpful often to think of an atom as having 4 parts on the outside. All right, so let's do the third step. Let's connect everything through bonds. Each time you connect 2 atoms together, that's called a covalent bond or molecular bond. Each time you make a bond, you are spending 2 electrons. So just to really make sure we're on the same page here, 1 bond equals 2 electrons, and more specifically, it's 2 electrons that are shared between 2 atoms. So if we spent 2, we have 6 left. Spend another 2, spend another 2, spend another 2. We have spent all 8 electrons. We are now down to 0 valence electrons. So we're going to hope that everything is at an octet, or in the case of hydrogen, at a duet. Right? With this approach, we look at the outside, then we go to the inside. So each hydrogen has 2 electrons on it. Okay, 2 electrons touching it or on the surface of it. All right, you can like even maybe do a Venn diagram sort of approach. Okay, this hydrogen has 2. This hydrogen has 2. 2, and 2. All of the outer hydrogens are at duet. They are good to go. All right, how about the center carbon? Now that we have found the outside to be happy, we want to look at the inside. And here's my Venn diagram for that central carbon. Other than hydrogen, everything needs to be at octet, 8 total electrons. Well, carbon has 2, 4, 6, 8 on its surface. So this structure is done. When you draw a Lewis structure, you do not need to draw like dots. You don't have to draw like Venn diagram circles. I just do that sometimes so that people can see octet rule and duet rule being satisfied. This would be the most simple way of drawing this molecule. All right. In my previous video, when I was talking about Lewis symbols, I talked about this so-called jigsaw puzzle approach. And again, I first want to say that it only works sometimes. It doesn't work all the time. All right, but it does work sometimes. In this video, I'm going to have a few examples where that jigsaw approach will not work. Okay, and because the jigsaw puzzle approach doesn't always work, some chemistry teachers will not teach it. They'll discourage it, or they'll just tell students to avoid it completely. All right. I'm kind of in the middle area. I see sometimes that it's helpful, and so I'm gonna kind of semi-teach it here. Here's the Lewis symbol for carbon. Oh, this is the jigsaw puzzle approach. Jigsaw puzzle alternate approach. Lewis symbol for carbon. For hydrogen number 1. Two. Three. I'm off screen. You know what? I'm going to move my head to the bottom left corner. I feel like, oop. What is going on? Here we go. Sorry, I'm probably not going to edit that out because I'm trying to get these videos out as fast as possible. And then hydrogen number 4. All right, so there's the Lewis symbols, and now we're going to just click them in place like we're building a jigsaw puzzle. And hopefully you can kind of just see the bonds kind of naturally happen, the 2 electrons being shared. And there's bond number 1, bond number 2. I'm using orange here. And then if you look at us building that connection, look, you'll get the same answer. Okay, so the jigsaw puzzle approach indeed works sometimes. Okay, just to really make sure you get what I'm saying here, these orange boxes, those have become my orange sticks. Okay. Apologies if I'm being a little bit excessive here in my explanation, but some people enjoy when I do that. I just want to make sure we're all on the same page. I won't do this every time. All right, there we go. Methane, and we did it with both approaches. This was on the left, a traditional approach. Which it kind of nicknamed check electrons at the door. And then we had the jigsaw puzzle approach. Okay, Let's keep going. Next example. Oh, I got page bleed through going on. I better do this. All right, we got ammonia, NH3. 1 nitrogen, 3 hydrogens. Nitrogen is in the 5 valence electron group. And then hydrogen's always a 1. Five plus 3. 5 plus 3 is 8 valence electrons. Nitrogen in the middle, it's never hydrogen. Place outer atoms. Connect with bonds. 2, 4, 6 we have spent. We have 2 valence electrons remaining after single bonds. All right, so the hydrogens are instantly done. Now we have to see if nitrogen is at an octet. 2, 4, 6, it needs 2 more. Well, we have 2 more left to spend. And so that worked out pretty nicely. 0 left. Okay, and again, we can do kind of a quick Venn diagram here, if you like. All right, if you wanted a jigsaw approach, then we would have our nitrogen Lewis symbol. 1, 2, 3, 4, 5. Oops, let me make that consistent with that one. 1, 2, 3, 4, 5. There we go. And then we'd have our hydrogens coming in. Connect them together, and you would get that same thing. Or what some people like to do, they sometimes like to show the different elements with different electron symbols. You could go that way too, like X's. And in your final Lewis symbol or Lewis structure, you could leave them that way if you wanted them to stay that way. Up to you. Kind of a weird way of showing bonds with just like electrons not as lines, but that's perfectly okay actually. All right, and some instructors will accept it that way as well. I know I would. This is totally good and okay in my book. Okay, or maybe you would just show the electrons, but maybe you would do away with the X's and dots and stuff. Whatever, they all mean the same thing to me. That means the same. That means the same. That means the same. They're all good. We're just following octet, so we're happy. All right, that was ammonia. Water. Looks like I need a new Sharpie. All right, so go ahead, count up water's valence electrons. Water is going to be one of those few structures where the first element listed is not the central atom. Okay. Oxygen is the central atom. Anyways, we got 2 hydrogens. We have 1 oxygen. I like to write oxygen's symbol as oxy rather than the O, so it doesn't look like I'm writing the number 10. That's just my preference. Oxygen is in the column with 6 valence electrons. Wait, I just did that. Whatever. 2, 6, 8 valence electrons total. Right, put O in the middle. hydrogen, hydrogen, 2, 4. Outer atoms are happy, go to the center. 5, 6, 7, 8. I like to work in pairs. I like to count in twos. All right, that's water's Lewis structure. All right, if you were to go to jigsaw approach, okay, I could have put the last dot there, or there, or there. Doesn't really matter. And then there would be your water structure. Okay, so it looks like Jigsaw worked there. Jigsaw is going to work on a bunch of these today, but again, it doesn't work every time. All right, next on our list is carbon tetrachloride. Notice I kind of did this box notation here so you could see that Cl is one element. Sometimes people will look at this, they'll look at like carbon, carbon, iodine 4. No, that's not what we meant. Okay. Capital C next to a lowercase l, that is a chlorine. Oh, there it is on the screen. So keep that in mind. It's not CCI4, CCl4. All right, carbon tetrachloride. We got 1 carbon and we have 4 chlorines. Chlorine, right there, 7 valence electrons. We got 1 carbon, 4 chlorines, so our subtotals will be a 4. And 4 times 7 is going to be 28. So we will have 32 valence electrons total. All right, pretty big number. All right, carbon in the middle. Chlorine, 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 chlorine. I just went ahead and connected them immediately. So you can see that I've spent 8 electrons immediately. 2, 4, 6, 8. 32 minus 8 is 24. We have 24 left. That's a T. All right, we go to the outside and then we look in. This is the first example where we have outer atoms that are not hydrogen. In the previous examples, we were used to going kind of straight to the inside because we had hydrogens. Not this time. We go outside, then we go inside. All right, so each chlorine has 2 electrons on it so far. See, you have a bond right here. You spent 2 electrons. That means this chlorine needs 6 more. That can be said for every chlorine. So we'll work in twos. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have spent all 24. We have 0 left. We know we got all the chlorines to octet. How about that central carbon? Well, when we made the 4 bonds, it got to an octet instantly. So it was fixed already from the beginning, and so this Lewis structure is done. All right. Will this molecule work with the jigsaw approach? Yes, it will. I'll leave that to you to explore. All right, next up, CHCl3, chloroform. So this is going to be similar to CH4. This is going to be similar to CCl4. We kind of have an in-between scenario where instead of 4 chlorines, one of them is a hydrogen. But you're going to see it's going to end up looking pretty similar anyways. 1 carbon, 1 hydrogen, 3 chlorines. 1 times 4, 1 times 1, 3 times 7. 3 times 7 is 21. Add all these together, it's going to be 26 valence electrons. Notice that we're getting an even number every single time. That's usually going to be the case in, I would guess, an average Chem 101 intro class. I haven't heard of an intro chem curriculum where you work with an odd number of electrons. Those are usually a radical species, and that's more of a general chemistry, principles of chemistry sort of course, not usually an intro course. Okay, so look for that even number. All right, if you don't have an even number at this level, you probably did something wrong somewhere. All right, 26 valence electrons. Carbon in the middle, we're getting pretty used to that. Spend 2, spend another 2, spend another 2, spend another 2. 26 minus 8 from 2, 4, 6, 8. We get 18 left. All right, each carbon needs 6 more. Well, we have, or carbon, I meant to say chlorine. Each chlorine needs 6 more. We have 3 chlorines. 3 times 6 is 18. We can see we're going to spend all 18 just like that. All right, if you don't math so fast in your head, that's okay. Just pair them out. First pair, there's 2, 4 electrons, 6 electrons, 8, 10, 12, 14, 16, 18. Done. Okay, maybe I did that too fast. Let's do the double check. Duet, octet, 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 and then the center, always go, whoops, outside in, always. Center carbon, yep, as octet. So indeed, that is done. All right, nitrogen trichloride. Okay. Oh, I went so fast I didn't even get the total. Total is 26 valence electrons. Spend 2, 4, 6. I have 20 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 2 valence electrons left. But we finish all of our octets on the outside. That means look inside. Look at the center. Nitrogen's at 2, 4, 6. It needs those 2 more that we have. Let's spend them. Done. Okay. All right, let's keep going. Chloramine. Okay. Wait, I just did that. So 1 times 5 is 5, 2 times 1 is 2, 1 times 7 is 7. 5 plus 2 is 7. 7 plus 7 is 14. All right, nitrogen, middle. Put on a hydrogen. Put on another hydrogen. Put on a chlorine. I like to draw things symmetrical looking. It's not a requirement. It's just, I like it that way. Oops, stray mark. All right, we spent 2, 4, 6. 8 left to go. Hydrogen, happy. Hydrogen, happy. H is for happy. Chlorine needs 6 more. Feed it. We have 2 left to spend. Nitrogen is still hungry. Feed it. Okay. And you're done. I always think of like children's books when I do this, like the Hungry Hungry Caterpillar. It was still hungry. Feed it, feed it, feed it. All All right, yeah, that's done. All right, next up. Got a lot today. If you want more examples, I'll send them to you. There are tons of examples out there. All right, we got hypochlorous acid. H won't be our central atom, so we can think of oxygen or chlorine. It's going to be oxygen. All right, oxygen is more to the left than chlorine. It also has a higher bonding capacity. So O will be our central atom. At the Chem 101 level, I think it would be reasonable for your instructor to tell you what the central atom is. I know if I gave this as like a homework or exam, a question, I would tell them the central atom. So it's oxygen. All right, we got 1 hydrogen, 1 oxygen, 1 chlorine. 1 times 1, 1 times 6, 1 times 7. 1, 6, 7. So that totals to 14 again. All right, so let's do this. We're going to put an O right here. Hydrogen there. Chlorine there. Make a bond, spend 2. Make another bond, spend another 2. So we've spent 4. We have 10 left to go. All right. Now let's stay disciplined. We can see that both oxygen and chlorine both need more electrons, but chlorine's the outer atom, so it gets the electrons first. Chlorine needs 6 more. 1, 2, 3, 4, 5, 6. 4 left to spend. Oxygen needs 4 more. Oh, good. We have 4 left. It's always worked out so far. Towards the end, that won't always be the case. Ha ha ha. We'll have a double or triple bonds coming to fix that problem. All right. But there is your structure for hypochlorous acid. All right. Yeah, this is like the smell of bleach. All right. When you buy bleach, it's NaOCl. You mix it with a little bit of water, you're going to generate a little bit of this. But anyways, that's a side tangent. All right, let's keep it going. We got formaldehyde next. Four, 2, and 6. And that's going to make 12 valence electrons. Carbon, middle. Hydrogen, hydrogen. And then we need to connect an oxygen. All right, so far we have spent 2, 4, 6 electrons. 12 minus 6 is 6. So we have 6 left to spend. All right, stay disciplined. Oxygen and carbon both are not at octet yet, but oxygen is on the outside, so it gets it first. Well, this is going to be our first instance of finishing octet on outer atoms, but not being done with octet yet for the inner atom. Okay, you'll see what I mean. So oxygen needs 6 more. 1, 2, 3, 4, 5, 6. We have 0 valence electrons left. All right, so the temptation may be, well, carbon needs 2 more, so give it 2 more. But we have an error. We have a problem. We have nothing left to give it. 0. We are empty. Okay. Does that mean we did something wrong? No, it does not mean we did something wrong. We are doing everything correct so far. This is going to be the first instance of tackling that step number 6 I had earlier. So earlier I had said something about double or triple bonds if needed. See, we were following everything. We did single bonds. We did outer octets. We were trying to do the central octet. but we had nothing left to give it, so we had to skip to step 6. So we're going to consider this double or triple bond option. What does that mean? Well, that means convert outer atom lone pairs into bonds. Okay, great, Josh. I don't really understand what that means. All right, so I'll have to show how that works. Again, converting an outer atom lone pair into a bond. So here's what I mean by that. I'm going to use orange here. These 2 electrons right here, as of right now, they are still stuck on this oxygen. But I'm going to turn those 2 non-bonding electrons, this lone pair here, I'm going to literally turn it into a bond. So here's kind of my before picture, and then here's my after picture. All right, that first lone pair, I just moved it over there. You don't have to box it. I'm just showing where I got it from. The second lone pair here, I now have it here. And these 2 electrons that used to be on only the oxygen are now right here, in between the carbon and the oxygen. And again, remember, each line represents 2 electrons. Let me clean this up. And I'll keep that one in orange. All right, and this would be the final structure. This is our first instance of the so-called double bond. So let's recap what happened. You may be feeling scared to turn 2 electrons into a bond. That may feel weird, and you might feel like, oh no, oxygen is going to lose 2 electrons. But it does not. Okay, oxygen's still okay. Oxygen's still okay. Check it out. In this first picture, the before picture, oxygen has 2, 4, 6, 8 electrons on it. All right, it's fine. It's good to go. How about this second picture? 2, 4, 6, 8. It's still 8. Okay, so the donating atom, your outer atom, does not lose electrons. Okay, that is a good thing. Whereas your receiving atom will gain 2 valence electrons in its count. Okay, let's prove that. Let's look at this carbon. 2, 4, 6, and now it has 8 because we made that orange line. Okay, again, beforehand 2, 4, 6, it wanted 2 more, but now through sharing it's able to experience 2 more electrons. So that's when you make the double bond, is when you're out of electrons but your center atom needs more electrons. All right, that was formaldehyde. Let's move on to carbon dioxide. All right, carbon dioxide. 1 carbon, 2 oxygens, and well, that's it. 1 times 4, 2 times 6, 4, 12, a total of 16. Carbon, middle. Bond oxygen. Bond another oxygen. We have spent 4. We have 12 left to spend. This oxygen needs 6 more. That leaves me with 6 left. This oxygen also needs 6 more. That leaves me with nothing left to spend. Oxygens are happy. The central carbon is not. Central carbon needs 4 more. It has 4 currently, 2 and 4, but it needs 4 more. So we're going to need to donate 2 lone pairs to this central carbon. All right. Nature in this situation will favor symmetry. So rather than taking 2 lone pairs from the same outer oxygen, I'm going to do 1 from each side. That one, I'll use red there, and then this one, I'll use blue. Whoops. And I'll stick with those colors to show the electrons that were turned into those double bonds, the second bonds. All right, so this would be our Lewis structure for carbon dioxide. Okay, I haven't talked about the jigsaw approach in a while. All right, and again, for those just tuning in or those needing a refresh from last time, that jigsaw approach does not always work. But again, I like to teach it slightly just so that people can kind of see the pieces coming together. All right, if I had a Lewis symbol for the middle carbon, it would be like that. For this outer oxygen, and then the other outer oxygen, and then hopefully from here, I'll use orange. You can see those double bonds kind of happening by forming these pairs. Sorry, I had to sneeze. Okay, those 2, and then those 2. And then, yeah, double bond, and then you would get that same result. Okay, great. All right. Starting to get closer to the home stretch. Let's do some diatomics. Okay, diatomics, they do not have central atoms. Or the other way you can think of it is you can just make one of the atoms your center atom. All right, hydrogen gas. 2 hydrogens, so that's going to be 2 times 1, 2 valence electrons. Here's a hydrogen, here's another hydrogen. Done. Instantly happy, each have 2 electrons being shared. Okay, let's do chlorine gas next. 2 chlorines means we're going to have 2 times 7. That's going to be 14 valence electrons. Chlorine, bond, chlorine. 12 electrons left after making that 1 bond. Each chlorine needs 6 more. Done. Are they octeted? Yes, they are. 8. 8. Okay, it's not a bad idea. It's often a good idea to do a double check on your octets, even if it feels like the molecule clicked together so fast. Okay, just good to be on the safe side. All right, oxygen gas. We have 2 oxygens. So that's going to be 2 times 6, 12. Oxygen, oxygen. We have made 1 bond, so we have 10 left. 1, 2, 3, 4, 5, 6. That oxygen's done. 7, 8, 9, 10. Uh-oh, we are out. But not to worry, we can turn that into a double bond. and we get that structure for oxygen. Okay, and then lastly we have nitrogen. 2 nitrogens is going to be 2 times 5, 10. First N, second N. Spend 2 electrons on the bond. We have 8 left to go. 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen's still hungry for 4 more, so we're going to do that and do that. Triple bond, first one of the day. Okay, and the jigsaw approach would work for each of these molecules. Okay, if you want a quick proof, let me do nitrogen here. And then here's our other nitrogen. It's gonna be a little bit messy, but here's bond number 1, bond number 2, bond number 3. I feel like I'm drawing a Golgi Bladder from like high school biology or something. Anyways, okay, and then you would get that same result. All right, we are entering the home stretch, and now with these final 2 molecules, we're going to show where the jigsaw approach does not work. Okay, at this point you may be like, jigsaw approach seemed to work every time, and again, it works a lot, but you'll see why we don't consider it the superior method. All right, enough talk, let's do it. So we have 1 sulfur, 2 oxygens for this is sulfur dioxide. Sulfur is 6. Oxygens also 6. So we get 6, we get 12. Sorry, allergies, I guess. All right, 18 valence electrons. Sulfur is going to be a central atom. It's more down compared to oxygen. It's a larger atom. Sulfur, oxygen, oxygen. Bond, another bond. We have spent 4, 14 left. Each oxygen is going to need 6 more, so that's going to spend 12. 2, 4, 6, 8, 10, 12. Two left. Oxygens are done. Go to sulfur. We have spent all of our electrons. We have nothing left, but sulfur is still hungry. So let's make a double bond. We have 6 pairs to choose from. Just choose one of them. It doesn't matter. Heck, in the next video, I'll show that this is not even the final structure. Oops, did I share too much? We'll just pretend this is the final structure. Tune into the next video to see why this is not the final structure. It has something to deal with the fact that I could have also chosen from the other side. I'll just leave it at that. Just for now, let's pretend this is the final structure. This is sulfur dioxide. And as promised, here is an example of where the jigsaw approach does not work. See, if you look at sulfur's original Lewis symbol, it's like that. Okay, we have a pair here, we have a pair here, and then I have a available electron there, and I have a available electron there if you're using the Lewis symbol bonding capacity idea. Oxygen actually has an identical Lewis symbol to oxygen. They're both in that same group. All right, here's oxygens. And then we did that one, let's do another oxygen. All right, so Oh, that was a little messy there. Let me keep my pairs together in boxes and my unpaired electrons in green circles. All right, so you can see here that this oxygen is searching to make 2 bonds, but this sulfur looks like it's only searching for 2 bonds. And then, so if we were to go with that idea of just connecting lines, then we would end up with like SO. But what about this third atom, the other O? It would have no place to go. So this is where I can say that the jigsaw approach indeed, unfortunately, because it's so fun to do, but is unfortunately inferior because it does not get us to a plausible structure. Whereas sulfur dioxide is going to have a structure, it's basically this. In the next video, I'll show how it's basically this, but not quite. But it's basically this, and the jigsaw approach would not allow us to get to this structure. All right, I got one more example for your consideration, and that's going to be carbon monoxide. This will be our last structure for this video. All right, so carbon monoxide is going to be interesting. We've seen carbon always with 4 bonds, and that's such a constant thing seen in chemistry that you can almost consider that law, almost law. But carbon monoxide is going to be one of those rare exceptions where you do not see carbon with 4 bonds. All right. So like if I was running a chemistry class, this would maybe be like a bonus problem because it deviates from what's normal for carbon. All right, so let's do it. We have 1 carbon, 1 oxygen. 1 times 4, 1 times 6, 4, 6. Get our total of 10 valence electrons. Carbon, oxygen. I've spent 1 bond, so I've spent 2 electrons. I have 8 valence electrons left to spend. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's still hungry for 4 more actually, so we're gonna have to do this twice. We're gonna get a triple bond. Okay. Carbon normally does not have lone pairs on it. That's weird. Carbon normally has 4 bonds, not only 3. That's weird. Yet this is carbon monoxide's structure. Okay. Weird exception. This does not work with a jigsaw approach either. All right, here's your proof. Carbon's ready to make 4 bonds in its Lewis symbol, but oxygen is only ready to make 2 bonds. Yet we see in the correct structure, carbon has 3 bonds, not 4. Oxygen has 2 bonds, or excuse me, 3 bonds and not 2. Okay, so we cannot jigsaw them together. Will not work like a jigsaw puzzle. All right, as a closing thought, I always seem to have a closing thought. I want to talk about hemoglobin. Hemoglobin, okay, protein in our body with an iron center. It's a metalloprotein, and it's for transporting oxygen. Right, you can see the chemical similarity between oxygen and carbon monoxide. But carbon monoxide is poisonous in our body because with a similar shape and similar chemistry, it can bind in place of oxygen, making it even worse. Carbon monoxide's bond to iron in hemoglobin is about 250 times stronger than that of oxygen's. Okay, that's what makes it a deadly gas. So, all right, hopefully this helps. We will build things into 3D in the next video. All right, thanks. Take care.